Hi, everybody. Professor Ghassemi here. Welcome back to another lecture on AI agents at Michigan State University. Today's lecture is about the practical use of these AI agents and the more foundational technologies, which are LLMs, in real-world settings. So we're going to be talking about how you evaluate their performance, how you think about the cost, you think through scalability requirements, and all those other things that are important for deploying in real systems. There's a set of first principles that you should follow when you're building any system that has an LLM at its heart, or I would even argue um, a vision language model or any kind of large statistical model at its heart. And among those first principles are two that I'm highlighting here. The first being you really want to think carefully about whether an LLM is needed for some, all, or none of your system's tasks. And that's because large language models, vision language models, and most large foundational models are not as cost effective as a combination of tool calling, generic code, and a well-structured database. That doesn't mean, of course, that they don't have a place within a technology stack, but like most things, you want to figure out the right place to deploy your large foundational models so that you're really getting a lift from them and they're not solving a problem that could be addressed by a simpler technology. Okay, so the rule of thumb that you can follow is to prefer non-LLM solutions whenever they suffice. And we'll talk as we go through some of the examples in the lecture today about what it means for a solution to suffice. Okay, so let's assume as you're designing your real-world LLM system, you have identified a subset of the tasks that you think really truly these require an LLM. I can't do them through just writing regular expressions or uh, calling Spacey to do some basic sentiment analysis. I need an LLM for this task. As you're thinking through the deployment requirements, there's kind of four categories of considerations that you'll want to keep in mind. The first is data, how you store both the structured as well as the metadata, um, and considerations around how you embed the unstructured data so that it can be retrieved at the point of answering questions if you're building a RAG system, for example. The second is tooling. So using and building tools for subtasks whenever possible, even if you're going to be using an LLM, it could be that the LLM, as we've discussed in previous lectures, could call a tool that does a specialty task, not only at a lower price point, but also more reliably than an LLM on its own can. And you'd obviously want to expose these tools to the LLM through an established protocol like MCP, which we've discussed in previous lectures. So both of these topics on the data and the tooling, these are things that we've actually covered in previous lectures. We've practiced them in the homework. But one thing that we've not covered and where we're going to be focusing today is on these last two elements. So in a practical setting, when you're choosing the model, the actual underlying LLM, be that Claude or Llama 3 or GPT-4o, how do you select the most appropriate model? And what you're going to see in the conversation today is that there's a set of public leaderboards that are available that will help us to achieve that. The second thing to keep in mind, which we've touched on in passing, but won't be going into in a lot of detail in this lecture, is you really only want to fine tune when you have a sizable question answer data set that's available. The third thing is you want to periodically review and adapt prompts as your models update. Okay, so these are the considerations for modeling. The last set of considerations here, which we'll also be talking about in the lecture today, have to do with evaluation. So that's developing internal test suites to verify your system's performance and estimating and monitoring the operational costs based on your expected system usage. Okay. So if you take nothing else away from this lecture, and I would even argue from this class, I would love for you to take away these main points for scaffolding a real system that you build. To help make these last two items more concrete, let's actually dive into an illustrative example that's based on actually a project I did a few years ago. And this illustrative example is meant to highlight the fact that when you're building an AI agent in practice, you have to balance cost and performance. And I'd like to step you through how you do that balancing. So, what's the problem? Well, let's assume that we want to extract a graph of all scientific knowledge that's been described in scientific journals, conference proceedings, and so on since 1996. And so you have a concrete kind of vision of what we're looking to do. Imagine you have a set of papers, like these grayed out images I'm showing you here. And these papers come from a variety of domains: the social sciences, genomics, behavioral sciences, human physiology, and so on. And what we're interested in doing, because we don't want to read all these papers, that would take us a lifetime and then some, we might like to extract something like a knowledge graph that could tell us what are the relationships between some of the items that were studied inside those scientific papers, like stress and age, for example, and how those end up impacting something that we might care about in a practical setting, like a person's measured cognitive abilities. When I'm under stress, don't perform as well cognitively. I also know there's some research that says as we age, cognitive abilities tend to decline. It's useful to know what's that mechanism of action, in this case, dendritic branching, that controls that decline. Why that matters is because that might inform how we go about developing treatments that stop this mitigating effect, which cause the decline in the cognitive ability in this case. Okay. So, long story short, we're interested in figuring out how we can extract a graph that models scientific knowledge, because looking at the scientific knowledge base as a graph might allow us to draw conclusions more easily than reading through millions upon millions of papers. In this case, something on the order of 64 million papers published since 1996. So, as part of needing to do this, not the whole task, but as part of needing to do this, we'll have to do some information extraction, right? We'll have to take a paper or a document, like I have here, and from it, I will need to extract some entities. Okay. So, for example, I might want to extract this formula here and this formula here. I might want to extract the lithium battery, electrolyte, and positive electrodes so that I can use those entities that were extracted from the text as nodes within the graph on the left. And then, as a function of what was specified here in semantic triples, I could use that to draw evidence associated with the edges. Okay, so this information extraction task is sort of the first step if we want to achieve the graph on the left-hand side. Okay, so at its simplest, one thing we might do is say, hey, why don't we just go take a state-of-the-art large language model, ChatGPT, Gemini, Claude, whatever our favorite is, and we can just feed those papers one at a time to this large language model. It can read the entire set. And once it's done that, we have all of our entities and we can move to the next step after that. Okay, sounds simple enough. The issue with this approach is if you do some math following the assumptions I've put in the bottom right-hand side of the screen here, which I'll spare you from, it would cost you something on the order of $6.5 million to actually read through all 64 million papers that have been published since 1996. Um, Given the current speed of a commercial LLM today, in terms of how quickly it can read tokens and how quickly it can write tokens back to you, the time would take something on the order of 100 years, probably a little longer than you'd need or you'd hope for. And of course, I would argue a really huge problem is you might wait this 100 years, having spent this $6.4 million, and you actually wouldn't know what the performance would be. You just handed the stack of papers, paid the money, and have to wait to see how well it does. So this is a problem, right? And what I'd like to do is we go through to understand the evaluation criteria for large language models is I'd like us to sort of double click on each of these three result areas, the performance, the cost, and the time, and see how there are ways with some systems thinking that we can optimize all three of these axes. Let's start with the first one, in many respects, the most important one, which is the performance. We don't even know what it is right now. So how would you know which LLM to use? How would you know what your anticipated performance would be if you chose ChatGPT versus Claude versus Qwen versus DeepSeek and so on? Well, the very first thing that you would want to do is start by checking a benchmark leaderboard. Okay. That's the very first thing you'd want to do. And there are many of these that are available online. I anticipate that as time goes on, maybe even in as little as a month from the time that I've recorded this, there could be not only new benchmarks that get added beyond what I'm showing you here from llmstats.com, but I anticipate that there will be even additional websites that will provide you with access to leaderboards associated with a variety of benchmarks, a subset of which come from scientific papers. Okay, in the case of llmstats.com, you can see you can come and search for a task or a benchmark of interest. They also provide you with sort of a breakdown in these little pillboxes here of how many particular benchmarks they have within certain categorical areas like general, role playing, speech to text, and so on. So there's a lot of benchmarks, more are growing all the time. And the first thing you'd want to do if you wanted to figure out which LLM is best for a task you're going to be solving is to check if there's a benchmark that's similar to what you're doing. If we were going to be extracting knowledge from scientific text documents, that would be a great place to start, right? We might go look if there's a benchmark out there that's done a similar task, see which LLM did best, and then we use that LLM. I had mentioned earlier there's more than one of these leaderboards. Okay, so another example of a leaderboard here is idpleaderboard.org. And I chose this one because they actually have a key information extraction leaderboard, which, as you can see from the description here, has to do with assessing a model's ability to identify and extract specific information from documents, such as names, dates, amounts, and other structured data. Okay. So that seems like, at least at the task level, close to what we want to do when we're taking those scientific documents and turning them into the knowledge graph, right? We have to extract the entities first. And so when we take a quick look at this breakdown of the leaderboard, it gives us a rank of various models in the second column. And at first glance, Gemini seems to be the best choice, right? It's ranked number one. Looks like that they've done this across a set of benchmarks on columns 4, 5, and 6 here. So at first glance, it appears that Gemini is the best choice. And from there, we might say problem is solved. But the issue here, and this is something you'll want to be aware of as you're looking at benchmarks on your own, is that this rank is based on an average score across the three benchmarks. You can tell because this little down arrow implies we've sorted the values here to achieve the rank according to the average across the three benchmarks shown to the right here. And not all of these benchmarks may be relevant for the task that we're interested in. Okay, as an example, this handwritten forms benchmark, as implied by the word handwritten, um, you know, may not be relevant because scientific papers are not handwritten. And so this benchmark might not matter as much to us as one of the other two. Your question to me very naturally would be, well, but hey, what are these benchmarks anyway, right? We can tell this one has something to do with handwritten information, but we don't really know much more beyond that. Fortunately, all of these benchmarks, anyone that will show up on a leaderboard, you can go to a search engine, type in the value, or probably even ask your favorite LLM, and you will get a description of what that benchmark was testing within large language models. And so what I've done here is for each of the three benchmarks that were shown on the previous table, NanoNets, DocIsle, and handwritten forms, I've shown what the primary use case was for those three benchmarks, and also my own assessment of how similar this use case is to, looking at scientific papers and trying to extract information. So between these three, looking at business document fields, I didn't think was particularly relevant. Doing OCR on form fields, like imagine you're a doctor's intake form, turning that into the appropriate structure digitally, like in Markdown, I also thought was probably not very relevant to what we need to do. But extracting information, maybe not so much on the layout, but definitely the semantic content of a document, I felt like that could be relevant to what we're doing. Not perfectly relevant, but somewhat. And so among these three benchmarks, it's very clear that docile or docile is the most relevant. Still not perfect, but definitely the best choice among the three. So if I come and I re-rank this now, as you can tell by the blue arrow here, so that we're putting this in descending order of the score according to docile. Now, the Gemini model moves to third place on this list, and you can see Quen 2.5 actually moves to first place. So this is a long-winded way of me saying that when you're trying to look at these benchmark leaderboards, it's really important that you understand the underlying benchmark, because those models that will pop to the top of the leaderboard depend very much on the task that's handled within the particular benchmark. You've got to think carefully about whether that task is or is not similar to the one that you're trying to solve, so that the models that you start investigating, in this case, we might start with Quen, are more likely to give you the best performance right out of the box on the get-go. Okay. Now, there's an additional challenge here, though, which many of you are probably going to face when you build these systems, in real use cases, in real companies, be that company your own, for a personal project, for an individual you work with or consult for. And that is that just like the case was here, there wasn't a perfect benchmark across the three that we were looking at. None of them had to do with extracting information from scientific papers. So too, when you go to solve this problem in real life, you're probably not going to find a perfect benchmark. You're going to be able to get a set of models that did well on a benchmark that was kind of like your task, but it won't be identical to your task. And because of that, in practice, you actually don't want to just blindly trust the first model on the list. You want to instead go take, let's say, the top N models on the list, and then you have to think about how you can make a benchmark for your task, maybe not as big as the official ones, but something that will give you confidence that Quen 2.5 in this case is the best among the players, and Gemini 2.0 Flash is not. Okay? So let's look through practically how you end up doing this. Well, the first step is you have to create a benchmark. And this should look familiar to you. This was the same example I gave a few slides ago, where you have some documents. Those are scientific papers in this case. And we were interested in extracting entities. So you want some annotated, labeled set of, given a document, that's the input to your language model. Here's the entities that come out the other side. Okay. So for every document, you have the corresponding entities. Once you have a benchmark, which would have more than one example, I'm showing you one here, you'd ideally have a large number of examples. You can then come and assess the top N models according to their performance on your benchmark. Or that is to say, you can take each of the inputs, pass it to a set of models, Gemini, ChatGPT, DeepSeek, and so on, and see how well they do in generating the entities that you cared about. Okay. You can do some detailed analysis to try to figure out if there were thematic trends in which model did better on which subtasks, and so on and so forth. I chose this pipeline here, which comes from a paper called P2L, which I've also linked down here, in case you'd like to use a tool that will do this assessment of the top N models in a semi-autonomous way for you. There's a little bit of setup to use the P2L pipeline, but it can do the assessment for you given a prompt, in this case this, and an answer. What are the performance of the top models to help guide your decisions for which model you should use? You could also, of course, do this on your own. You'd have to write, a for loop, obviously. You'd have to set up all the keys, but it's not terribly difficult to do on your own either. The really important thing for me to note here, though, is if you're going to, in practice, be doing an assessment or comparison of these models, we've sort of glazed over the fact that you need a formal way to define the performance. Okay? I'll be more clear. When we look at this document here in this example, and we look at the entities extracted here, how exactly do we score if one model did better than the other? Do we say, well, I'm just going to look at accuracy. So here I have a set of ground truth entities. Whatever fraction of them I find, that's the score. Or do we penalize more for a false positive? So for example, the LLM could add an extra entity that didn't belong here. That's a false positive. Or there could be a false negative. So it could remove one of the items from the list that should have been there. How do we handle those cases, right? Are those equally bad, or is one more bad than the other? Those are the considerations that go into when you're building the measure of performance you should think through. So I'm showing you here an example of the score that sort of leans into what we were just talking about with the false positives and false negatives. If you've ever done a classification task, which I hope many of you watching this video have, you'll know that you have like sort of 4 possible worlds when you're trying to detect if something is true or false, or in our case, if it's there or not there. Okay? Figuring out if an item is or is not on the list, true or false, is binary in that sense, right? So we have 4 possible universes. One where we predict that an entity was going to be on the list, or rather the LLM does, and it was on the list. And we can count up the total number of times that happens across our benchmark. Okay, so these are great. We want these to happen. We can also count the other side, which is what are the things that we didn't want to happen? We didn't want to happen, as in not show up on this list, that in fact did not show up on this list. Okay, and we can count those. There's probably going to be a lot more of those because the hypothetical set of all entities is going to be very, very large, right? There's a ridiculously large number of entities we could extract and did not extract. Okay, and then we have those off diagonals that we just spoke through a few minutes ago. So false positive would be the LLM reads this document and it generates an entity on this list that shouldn't have been there. And that could happen some number of times. And then the fourth option is the LLM omits an item that should have been there on the entity list. So in this particular case, each of these 4 possibilities, these 2 here and these 2 here, we can also associate a cost with these, or a payoff, if you will, for the LLM doing the action or not. So the best way to understand this is through doing contrasts. What you're going to notice about the ones in red here, these are the bad things, right? Things we don't want to happen. Notice that they're negative. The numbers here are negative. Now, I chose these negative numbers. They're just completely hypothetical. They're just exemplary. But what really matters is here, I'm saying that a false negative, so dropping something from this list that should have been there, is twice as bad, twice, because negative 1200 is twice negative 600. It's twice as bad as adding an item to the list that shouldn't have been there. Okay? So I define that here in my score, right? Through the way I've set up this ratio. I also, through the way I've set up this ratio, say that having a false negative, if I have one of those, it basically cancels out the payoff I get from a true positive. You see that? Because one is a positive version of the other. Okay. I also say here that Having a true positive is worth 3 times more than a true negative. Why? Because the true negatives are those are much easier to get. In fact, 400 here is pretty generous. This should probably be something very, very small, like 1, or maybe even 0. So when you have these 8 numbers, the true negative, the payoff for the true negative, the false negative, the payoff for the false negative, and so on, you can take the dot product of the values that fell into the confusion matrix and their corresponding payoff values, which is what this equation shows you, to compute a score. You can denominate that score by, let's say, the total number of predictions or the sum of all the values in this confusion matrix, and you can sort of average out what the performance is across all of the predictions. So this is an example of how you generate a quantitative numeric score that goes beyond kind of a simple heuristic that a benchmark might give you, which may or may not translate into your scenario. And this becomes extraordinarily important in practice when you're doing this in a practical or an industrial setting, as an example, because typically the costs associated with these 4 kinds of mistakes are drastically different. And when you're doing the assessments of the LLMs, or any method for that matter, you want to account for those differences. Okay, so let's assume we went through that process. Remember, our objective was to take some papers across a set of domains. We want to generate this graph. So let's say we went and we looked at some LLM benchmarks. We took leaderboards that were attached to those benchmarks. We selected a set of models. We identified some scores, such as the one I showed you before, so that we could finally measure this performance. Maybe the benchmark tells us it's estimated at 79.6, but we run our own experiments with our own smaller testing set and determine it's actually around 78. Okay, so the first, and I would argue in many ways, the most important question to answer about the performance is now solved. We have a way to take this hypothetical problem, which we've not solved yet or tried solving yet in a big way, and understanding just how well we're going to do at extracting the entities here, or the nodes for the graph. The issue here still remains, of course, that I don't think any of us are betting on being immortal, at least not anytime soon, and so we'd need to make this faster if we actually wanted a chance at generating the graph in a useful amount of time. And one easy way to do this is to simply take, because of the nature of the task, it's taking a document, extracting content from it, we can parallelize this. If we were doing it as humans, we could pass it to one paper to each of a set of humans and do it in parallel. So too can we do this with an LLM. So if we had 100,000 state-of-the-art LLMs extracting these relationships, it would take us 9 hours instead of 100 years, right? That makes it a little more tractable now for us to use this output. The issue, of course, remains that whether we have one LLM do it over 100 years or 100,000 LLMs do it over 9 hours, those LLMs all have a cost associated with their inference, their input, and their output tokens. And that cost will very quickly become prohibitive. You can see $6.4 million is definitely not something I'd be willing to pay. And this is where, from a systems perspective, thinking through the trade-off between the size of the model and the performance is really important. So balancing the cost and the performance becomes very important. There are scenarios where just changing a model to a slightly smaller model and doing a tiny bit more with your prompt or fine-tuning can reduce the cost by an order of 50, like 50 times cheaper, and without too much impact on the overall performance. This is a hypothetical number. In reality, it may be a little bit more than this, but there are scenarios that I've dealt with in practice where there's been no change in the performance, and or a very small change in the performance like I'm showing here. but you get these significant changes in what the practical cost would be to use the tool. So always ask yourself, or at least run the experiment when you've identified the leading model on whatever leaderboard and benchmark that you're looking at, be it yours or an official one from a leaderboard. Make sure you've also assessed how well a smaller large language model can do, so that if you need to process a large volume of requests or documents or inputs, you're spending, in this case, in the hundreds of thousands of dollars instead of the millions of dollars. Now, I would argue that even though cutting the cost down by 50 is fantastic and losing about 1% of our performance is probably worth that huge reduction, that price is honestly still a little too high. And so this is where the systems thinking can really help you. Understanding your problem can help you. If we're trying to extract information about relationships espoused within scientific papers, the unique findings within a scientific paper are probably going to show up somewhere in this results section. So if this is the breakdown of what exists within a scientific paper, each of the various pieces, the results here that I've highlighted is probably where the newer things are going that were unique to that paper's contribution to science are going to show up. And so we don't need to read the whole document. We can just, use a parsing tool calling, to cut out just the results section of the document, and that's what we can pass to the LLM. Now, because those results sections are much shorter, they're about a fifth of the length of the whole document, give or take, we'll be able to cut this cost down from hundreds of thousands of dollars to tens of thousands of dollars now. And of course, if we keep the number of LLMs the same, we're also going to see a reduction in the total amount of time. So that's pretty nice. We could actually go even further with this, depending on what our constraints were, and look at the abstract of the study, which is supposed to be a very short kind of 200 to 350 token description of the contents of the science, just within the start, typically, of a manuscript. And so we could use that to sort of cut the tokens down now to less than $10,000. So not even in the tens of thousands, we've gotten down to just the thousands. So what you should take away from this is that through carefully choosing the LLM, figuring out how we measure performance, and thinking about how to do this in practical cost settings in light of the problem we were going after, we can take a task that would have at the outset seemed like it would take 100 years and cost $6.5 million into something that could take us 24 minutes and cost us $5,000. So that's a pretty nice, I think, change. So with that motivational example out of the way, I want to spend a few minutes talking about formal approaches you use when you're evaluating large language models. What you noticed, I hope, as we were going through that motivational example, was we spent some time talking about how you generate the score, the scoring function. We spoke about time and we spoke about cost. Those are all things that you would use to evaluate the viability of an LLM solution. The aspect that we've not spoken as much about are the more qualitative evaluations of LLM outputs. Okay, so recall that when we were dealing with our scientific literature large language model assessment exercise just a few slides ago, we said we can take a formal score and we can use that formal score of the number of true positives, false positives, and so on to figure out how well a model is working on the task. The issue is there's going to be some problems like summarization, for instance, or the assessment of whether a book is well written or not, that you can't really generate a confusion matrix for that. You can't easily put it on a numerical scale. It requires qualitative judgment to get the answer. And in scenarios where qualitative judgment is required, you're going to be using one of these two other evaluation approaches. Either you'll have humans look at the output of your, um, your agent or your language model, or you'll have another LLM look at the output of your agent or your language model. When a human does this, it's called straightforward human evaluation. When an LLM does this, it's usually described as LLM as a judge. What I've included here are, for each of the three evaluation approaches, the scoring, which we went over in an example, and the two that we've just discussed now, human versus LLM evaluation, in what context these tend to work best, their limitations, and how you can mitigate some of the limitations here. I'll voice over a couple of these, and then I'd like to show you a little more concretely how these first two items end up playing out in practice. So first, when do these work best in practice? Well, starting with the formal scoring, if you have a structured task with a clear answer, like the information extraction task that we were looking at in the motivational example, great, you should use formal scoring. If we have a way we can measure this, let's just use the measurement to tell us what's best. If you're dealing with qualitative tasks that need a lot of judgment or nuance, and it's not too big, you're not going to be generating answers from this system in, millions upon millions of instances, then human evaluation of the output is probably tractable. If you have to do it on a large scale subjective task, that's when you're going to have to use an LLM as a judge instead. The limitations, I think, of human versus an LLM judge is pretty intuitive. Human beings are expensive, and they can also be inconsistent. And then the LLM has the issue that it could be biased, right? And it can also be inconsistent. Formal scoring, of course, has the limitation that it can miss meaning and or context. There are a couple of ways that you can mitigate the limitations of each of these. For the formal scoring, we actually discussed it as we were going through the motivational example. You can add cost weights. So instead of just naively looking at something like accuracy, you can break down the confusion matrix, assign a weight to each of the possible outcomes, and use those weights to give a more nuanced measure of the score. If you're going to be using human evaluators, you should plan to have multiple evaluators and measure their agreement formally through example, the kappa score. If you're going to use an LLM as a judge, you'll need to, every once in a while, have cross checks with humans and or other models that were trained ideally in different contexts so that you can basically emulate the kappa score that you would get if you had multiple human raters looking at an output. I wanted to break down here in a diagram how the use of human and LLM judges occurs in practice, similar to how we did for the formal metric here on the left when we were talking through the motivational example. Because we already discussed this, I'm going to skip over it. We're going to focus instead our attention on the content here on the right. So if you've run your system and you want to evaluate the outcome, if you're going to be using a human or an LLM to judge the quality of that outcome, the first thing you'd have to do is set up some annotation guidelines. So that's the set of rules that you want your language model to follow or your human to follow when performing the assessments. Like, write out a rubric. What do you want it to pay attention to when doing its qualitative assessments? You then would want to pass that annotation guideline to 1, 2, 3, n, however many people and or language models you can to perform the assessments per the annotation guidelines. You would collect all of those annotations that were performed, and you're going to calculate the inter-rater agreement metric. That could be the kappa score or some other inter-rater reliability measure that you care about. If the agreement metric is reached, then you're done. You move forward. if the kappa score or the measure of agreement between these three annotators up here diverges a lot, they have vastly different opinions on whether your AI agent responded appropriately or not to a set of user queries. In this case, you need to identify where are the disagreements, and you must, regardless of whether you're using a human or an LLM, have some kind of review to update the guidelines and annotations so that this process can be started again. I think this is the one piece of the process when you're using a human or LLM judge that there's no way to avoid really human input, because what happens here will dictate how the annotations from either the human or the LLM judges occurs downstream of that. Okay. If you're going to be using a human or an LLM as a judge, there are some very important limitations that you need to be aware of when doing those evaluations. And the best way for me to make you aware of those limitations is through, I think, an example. So imagine we have the question, what percentage of data science jobs require Python? And you can see here, there's three possible answers, A, B, and C. And the challenge is that even for an expert, so I teach computer science as a professor, so even for me, it's not obvious just by looking at these three options, 57, 78, and 82, which of them is the right answer to this particular question. I need more information to make a justified decision. The most likely answer only really becomes clear if we know the data and the methods that were used to generate all three of these numbers. So, for example, I could tell you that these first two numbers, 57 and 78, were sourced from the World Wide Web. And I could tell you that the third number was sourced from, let's say it's a knowledge graph that aggregates over Fortune 500 company job postings. Okay? Even with this level of information, though, about the methods, you still don't have enough knowledge that you can figure out which of these three is more likely, because it depends, for example, on what the source was here, right? These are both sourced from the web. Well, which source? It's only after we add these details about the underlying primary sources, their timeliness, their sample sizes, and their methodology that we can really reason over these about which of them is the most trustworthy. So for example, this first source, 57, comes from a study of 1,000 job postings from Monster.com in 2024. The second one is a 2022 Kaggle survey with about 24,000 participants. And the third one is from 960 or so data science job postings from Fortune 500 companies in Q3 of 2025. So with these three, and looking at what they have in common, the year, the source, and the method, we could come up with a score, right? We could come up with a score to identify which of these three is most reliable as a source in a way that just a human looking at it may not be able to get to give you the answer. Okay? So the whole point of me taking you through this is when you're doing your evaluation of LLMs, anywhere and everywhere you can, try your best to figure out a way to measure the performance through a score, through an accuracy, a reliability. If you can ever avoid it, um, it's better not to use human assessors or LLMs as a judge because they may not know just by looking at these three numbers which one is correct or not. So I think I've made the point pretty clear. Like if we were looking at all three of these, and we did want to use a human evaluator, it might be important to not just provide the three numbers, but to provide to the LLMs the information on how these three numbers, or the humans for that matter, how these three numbers were arrived at. What was the underlying methodology used to surface this? Because knowing that this data comes from Fortune 500 companies from Q3 of 2025 makes it more trustworthy, perhaps by some scoring or measure. And we can use that to get LLMs that do better on the tasks by making them aware of this underlying detail. Or we can, at a minimum, score the performance of LLMs if this information is not available at the time of inference. Okay, so the lesson I want you to take away, zooming out, is that if you're trying to identify a source's general value, it has less to do with the performance on any one input. It has more to do with its utility across inputs. So in our case, this graph is more consistent from a results perspective than just searching the web, which is going to give you a different source with a different method each and every time you use it. And this is not just a phenomena that I'm pointing out here in this class. This is coming from and echoed by a lot of the research that's happened from the large companies that are building AI agents in practice. So as you're probably aware, deep research, which is the tool that OpenAI has made available, which in an agentic way searches the web, does chain of thought reasoning with multiple LLM calls to generate a research-backed response to a query that you ask of OpenAI. That deep research tool is not flawless. It still makes mistakes. According to OpenAI's own reports of their performance on key benchmarks like BrowseComp, they only get a performance of around 51.5% out of 100, right? On tasks where the answers to the questions are available directly on the web. Okay. So I say all this because being aware of this performance is important when you're designing a system in practice. It's important for what kinds of checks and balances you place on your AI agents, is knowing how well you anticipate them to perform in practice. So that's it for today's lecture. I hope this overview was helpful. Key thing I want you to take away, look at benchmarks and leaderboards first. Build your own evaluation sets before trusting what a benchmark or a leaderboard tells you. It doesn't have to be huge. Even if it's a few dozen annotated examples, that's useful. When doing the assessment of the LLMs, try to build a score of some kind. If and only if you can't build a score, should you use an LLM or a human evaluation? If you're going to use an LLM or a human evaluation, make the reasoning associated with the choices that the LLM made clear, so that when a human's looking at the decision that the LLM made, they don't have to choose between just the two decision points, but they can choose between the two decision points and the underlying reasoning and sources that were used to arrive at those decision points. I hope that makes sense. I'll see you in the next video.